Hello students, myself Professor Ankur. I welcome everyone for the GATE theory session on analog circuits. Today we are going to discuss an important topic, oscillator using op-amp and triangular wave generator. This is our fifth session on operational amplifier and applications. Let's start with the session now. So the first circuitry that we are trying to interpret here, it is called as Wien bridge oscillator. It is also from the family of RC oscillator, but it is not an RC phase shift type oscillator. The main important point we need to understand here is the Wien bridge oscillator is an RC phase shift oscillator, introduces 180-degree phase shift during the amplification stage, while the Wien bridge oscillator are using non-inverting amplifiers. So there is no phase shift in the feedback network. So what do you mean by this statement? Very simple logic. The connections that we are trying to realize here in Wien bridge oscillator, the amplifiers we are trying to use here in Wien bridge oscillators are giving 0-degree phase shift. And that is the main reason the Wien bridge circuitry, when it is a part of the feedback circuitry, it will also produce 0-degree phase shift. Implies the concept of Wien bridge oscillator is applicable to non-inverting amplifiers, those circuits which don't give phase shift from input to output. And hence, even in the feedback path, when the Wien bridge network will be connected, even that network will not give any phase shift from input to output for that network. So that is the reason the overall phase shift for the entire loop will remain 0-degree. As far as the Barkhausen's criteria is concerned, the total phase shift for the entire loop has to be 0 or 360-degree, and the magnitude, or you can say the product of the loop gain, AV into beta, where AV is the gain of amplifier and beta is the gain of the feedback circuitry, the product of the gains, or you can say the total loop gain, should be unity. So with that logic, a Wien bridge circuitry was actually realized. When you clearly observe the Wien bridge circuitry, you can see a combination of resistor and capacitor in it. So it is basically a part of an RC series network and a RC shunt network. So the feedback circuitry is having RC series as well as RC shunt. In another understanding, we can say that it's a combination of a lead and a lag network. So the overall lead lag impact will be as good as no change of phase from input to output. So that is the basic background of the Wien bridge oscillator circuitry. Whereas we talk about the other family of RC phase shift oscillator circuitries, there the amplifiers that they will be using will be inverting amplifiers, and because of this, it will be the duty of the feedback circuitry to produce the necessary phase shift of 180-degree. So this is the basic logic of Wien bridge oscillator circuit. Now, when I talk about the gain of the circuitry, the gain of the amplifier will be defined as 1 plus RF by R1. To satisfy the condition that A beta has to be equal to 1, so the gain of the amplifier will come equal to 3. Under that logic, 1 plus RF by R1 can be taken equal to 3. Hence, RF by R1 will be taken as 2. So the value of RF should be equal to twice of R1. So this is a small understanding regarding the gain of the amplifier circuitry, where the gain of the amplifier circuitry will be having the value 3. So 1 plus RF by R1, where RF is the feedback resistor and R1 is a resistor, the other resistor. So the RF by R1 value will be coming equal to 2. So the value of RF, it should be twice of R1. That is the basic understanding of the amplifier gain A. Frequency of oscillation for the Wien bridge circuitry will have the value 1 by 2 pi RC. The components are selected such that the two resistances R1 and R2 will be considered equal to R, and the two capacitors C1 and C2 will be considered equal to C. Hence, when we talk about the frequency of output, it will be 1 by 2 pi under root of R1, R2, C1, C2, where R1, R2 will be taken as R and C1, C2 will be taken as C. Hence, the output frequency will be 1 by 2 pi RC. So if the gain of the amplifier circuitry is going to be 3, then the gain of the feedback circuitry will be as good as 1 by 3. Then only the value of A into beta will be equal to 1. So this is the basic requirement of the Wien-Bridge oscillator, that whenever you select the RC components, the two resistors and the two capacitors can be considered equal, and the frequency of oscillation can be taken as 1 by 2 pi RC. The gain of the amplifier using op-amp will be considered as 3. So the value of the gain 1 plus RF by R1 will be equal to 3. So RF will become twice of R1. This is all because the amplifier that we are using is of the type non-inverting. The frequency of oscillation will be 1 by 2 pi RC. So the advantage that we get here, that this is going to give you the best possible sine wave, and it is also used for various applications in the concept of audio frequency range. The disadvantages, if the op-amp is used, then we get an advantage, but if transistor amplifiers are used, then we get less stability. So the transistorized amplifier, in the concept of Wien-Bridge, they will have less stability compared to the op-amp circuits. Op-amp circuits will give you better stability. So that is the only disadvantage of the circuitry if you try to realize it using transistorized amplifiers. When we talk about the RC phase shift oscillator using op-amp, here the logic is very clear that the amplifier that we are going to use will be of the type inverting amplifier. So the amplifier will give us a phase shift of 180 degree. If that is the case, the feedback section should also give us a phase shift of 180 degree. And to satisfy our requirement, we will be using 3 RC section, where each RC section will give us a phase shift of 60 degree. So 60 degree plus 60 degree plus 60 degree will give us a value of 180 degree. So this is under a standard assumption that all the components of the circuitry, that is all 3 capacitors and all 3 resistors, are having same value. If you go for a different value combination, that is also possible, but the rule is the total phase shift should come out in some or the other form equal to 180. It cannot be less than 180, it cannot go more than 180, because the inverting amplifier will 110% give us a phase shift of 180 degree. The frequency of sustained oscillation under this concept of RC phase shift oscillator using op-amp will give us a value of 1 by 2 pi RC root of 6. So when I talk about the magnitude of the gain will be RF by R1, which will be equal to 29. So RF should be 29 times R1, and the gain of the feedback section, that will be beta factor, that beta factor will be equal to 1 by 29. So overall, which will be satisfying the Barkhausen's criteria, we will get the value of AV into beta as unity, and the total phase shift for the loop will come around 360 degree, which is the basic requirement of any amplifier circuitry coupled with a feedback network to work as an oscillator. So this is the basic concept of RC phase shift oscillator using op-amp. A small conclusion regarding RC oscillator and RC phase shift oscillator. RC phase shift oscillator using op-amp are utilizing 3 RC networks, whereas a RC oscillator circuitry using the concept of Wien-Bridge is using a combination of RC series and RC shunt. Both the logics are completely different because in both the cases, the type of amplifier that we are using is completely different. So we have to be very careful with the equations and the pattern that we are used to get the waveform properly. Now, the next concept is actually important. We are going for a triangular waveform generator. So here, when we talk about a triangular waveform generator, we have actually seen a square wave generator in the previous session. So the first circuitry is a part of a square wave generator. So a square wave generator will generate square wave signals which will range from plus Vsat to minus Vsat. This output will be given to an integrator, and on integration of square wave, we get triangular waveform. So the second form of arrangement is the lower circuitry. So in the lower circuitry, the first op-amp is also working to produce plus minus Vsat, and the output of plus minus Vsat will be given to an integrator which will give us triangular waveform. So the first amplifier is going to work like a basic comparator because the feedback loop impact is positive feedback. So the value of the non-inverting pin potential will be compared to the inverting pin potential, where the inverting pin potential is 0 volt. So whenever the voltage of the non-inverting pin potential, that is now node P, is greater than 0, the output of the amplifier A will be plus Vsat, and on integration of plus Vsat, the second circuitry will produce a ramp voltage that will be defined as minus of Vramp. Whereas when the node potential P goes slightly below the 0 value, automatically the inverting pin will be greater than the non-inverting pin. The output of amplifier A will be minus of Vsat. That time the second circuitry will integrate the energy to produce positive Vramp. So overall, if you observe, both the circuits are giving us a similar logic where the output is going to be a triangular waveform. So now let's understand what happens in the second circuitry. So in the second circuitry, we are assuming that if the output is initially plus Vsat for the amplifier A. So initially we are assuming that the output of the amplifier A is going to be plus Vsat. Then due to that impact, the output is going to be going to minus of Vramp. So now we are trying to get the voltage of node P that will be compared with the inverting potential, that is 0. So for that we need to go for a small calculation. So the small calculation will be with respect to an understanding that the amplitude of the square wave will be varying between plus minus Vsat, and the amplitude of the triangular wave will also decrease. It has to decrease, it will be less than the value of the square wave logic, and with respect to increase in frequency, the output of the triangular waveform will also decrease, and vice versa. And this is all because of the reactance of the capacitor that is varying with respect to changes in the frequency. So now what we need to understand here is, we were assuming that initially the output of amplifier 1, that is amplifier A, is going to be plus Vsat. So because of this, the second amplifier will integrate the energy and will produce minus of Vramp. So when I try to apply the node voltage of point P, the value will come as minus of Vramp plus R2 by R2 plus R3 into plus Vsat minus of minus Vrap. So it's a very simple fundamental of you can say voltage divider, where the drop across R2 plus the value of the output will be considered. So on that addition effect of the drop across R2 plus the ramp voltage, that voltage will be somewhere around 0, so that the output of the first amplifier can either be plus or minus Vsat. So for typical calculation, we are taking the value to be equal to 0. When we equate with the value equal to 0, we get minus of R3 by R2 plus R3 into Vram. We will get as minus of R2 by R2 plus R3 into plus Vsat. So overall, if you observe, you will get the value of Vramp as R2 by R3 into plus Vsat. On similar lines, you will get a value of minus Vramp as minus of R2 by R3 into minus Vsat. So from this, we got the value of plus Vramp and minus Vramp. So the total output peak to peak will be the potential difference between the two ramp peak values. So automatically it will be twice of R2 by R3 into Vsat. That will be the output VO peak to peak. Now the output that we got as VO peak to peak is basically an integration of a plus Vsat or a minus Vsat for half the time cycle. And that's the reason the VO peak to peak value can be equal to minus 1 by R1 C1 integral 0 till T by 2 and minus Vsat dt. So here we are assuming that we are actually integrating the minus Vsat so that the output will reach to plus Vramp. So for this, VO peak to peak will come out to be Vsat by R1 C1 into T by 2. So the value of T will come as twice of R1 C1 VO peak to peak by Vsat. On substituting the value of VO peak to peak as twice of R2 by R3 into Vsat, the Vsat gets cancelled, and we get the time period of the output as 4 times R1 R2 C1 by R3. So the frequency of the output will be R3 by 4 times R1 R2 C1. That will be the inverse of the time period. So this is how you calculate, or you can say, using this basic formula, we can design the circuitry as per our convenience and as per our component values. So this will help us in producing a waveform of frequency f and a time period t.